was in glycolysis. My input was what? My output was what?
4.
Okay, and then we also have to start thinking in terms of ATP equivalents. So what other thing do I get out of glycolysis?
GTP?
NADH. How many of them?
2.
Okay, so my net was 2 ATP plus 2 NADH. For 2 pyruvates. Going to 2 acetyl coenzyme A's. And so this is entry to the CAC. What's my energy input?
2 GTP? Or GDP?
It's a trick question.
Oh.
Thanks.
Sorry. How about output? I get an NADH. And since I have 2 acetyl coenzyme A's, I'm going to get 2 NADHs. So my net now is 2 NADH. So if you want to, it's 2 acetyl coenzyme A's. If you want to, you can, in parentheses, so we are keeping track of our carbons. Make it lost a couple carbon dioxides there. Okay. For 2 acetyl coenzyme A's, going to 2 oxaloacetates. And if you want to keep track of carbon dioxides. So this is now the citric acid cycle itself. Do I have any input?
NAD plus?
No,
No?
0 again. Okay. How about output? I get some GTP, yeah. I also get, sorry, letter? NADH, and I also get
FADH.
FADH2. Yeah. Okay, so I get all those things. How many NADHs do I get per turn of the citric acid cycle?
3.
2.
Around there.
1.
5.
Between 1 to
Oh
5.
dear.
How many hydrogenases did I have in the cycle?
Oh, 3.
3.
Yeah.
3, okay, so okay, you're going to get 6 NADHs. Because we have 2 acetyl coenzyme A's going in. How many FADH2s? 2. 1 each. Oops. 1 for each turn. How many GTPs?
2.
Okay, so everything's doubled because we got 2 acetyl coenzyme as well. So, and then your net. Same thing. All right. Conversions for ATP equivalents. When GTP equals how many ATPs?
1.
When FADH2 ATP, and for the longest time they used to teach 2. They would round that and say 2, but our electron transport chain and oxidative phosphorylation isn't quite perfect. So it actually takes more than just those 2 electrons to get the 2 ATP, so it's really closer to 1.5. NADH, they used to teach it as 3, but it's really closer to 2.5. So if you go look in older books, or maybe if you learned it in high school, you might have learned it as nice round numbers instead, but we're going to do fractions. So these we get at the end of the electron transport chain and oxidative phosphorylation, which I think is the next chapter. So oxidative phosphorylation, so what kind of conditions do you need to be under in order for this to happen? Anaerobic. I would probably just spell that perfectly. Oops, no, not anaerobic.
I was gonna say.
Aerobic, sorry. You have to have oxygen, so this is aerobic. Okay. So I want you to tell me now the total expected ATP from 1 glucose. Calculate that.
$22.
How many?
22.
Maybe something somewhere. Maybe missing something somewhere. Oh, yeah. 32. 32. Okay, so if I do some subtotals here, how many ATP do I get?
2.
2. So I have 2 ATP total. I have 2 GTP total. I have how many total NADH? 10. And how many FADs?
2.
Okay, so this is just times 1 times 1 times 2.5 times 1.5. There we got it. So 2 plus 2 plus 25 plus 3.
Yeah.
Hopefully equals 32. Okay. Alright, well that's pretty good. Better than glycolysis. Glycolysis we get 2.
Yay.
So, you know, when little critters can do aerobic respiration and there is oxygen around, that is preferred. So if you want to force fermentation, you have to force that anaerobic environment. Okay, one more topic for today before our activity, and that is pathways in and out of the citric acid cycle. Cataphoratic. What does the name suggest?
Catalysis.
What do
Catapholism.
pathways do?
Catabolism?
They break down.
They break down, yeah. They're the cannibals, they're breaking down. So cataphoratic pathways of the CAC, these deplete CAC intermediates. But the confusing thing here is that, okay, we're decreasing or pulling away citric acid cycle intermediates, but the purpose is an anabolic one. They're used in biosynthetic pathways. For other things. We've talked about one. What do you know that you can synthesize that involves a citric acid cycle intermediate? Or what biosynthetic pathway have we talked about? Sorry? Gluconeogenesis, yes. Okay. So gluconeogenesis. This is synthesis of glucose. Okay. What were we turning into glucose? What's the start of that pathway? Pyruvate. So this starts with pyruvate, which is not a citric acid cycle intermediate, but what is pyruvate turned into in my gluconeogenesis? Oxaloacetate. But is converted to oxaloacetate. Kind of that first step. Thus, oxaloacetate can be pulled from the CAC to make glucose. Okay, there is one potential problem with that. Where is oxaloacetate in the citric acid cycle? Where is it located?
The very beginning, or the very end.
Mitochondria. Where does gluconeogenesis happen?
Cytosol.
How do I get oxaloacetate from the mitochondrial matrix to the cytosol?
You convert to the malate.
Shuttle, yeah. Okay, so it must travel via the malate aspartate shuttle. Okay, so oxaloacetate gets converted to malate. Malate can cross the membrane, and then malate gets turned back into oxaloacetate. But I can deplete citric acid cycle intermediates to synthesize glucose. If I'm desperate for glucose, I can do that. One thing to keep in mind is that by depleting one citric acid cycle intermediate, you're really depleting all of them. Because it is a cycle. Each one gets turned into the next thing in the cycle. So if I pull one out, then I'm actually dropping the concentration of all citric acid cycle species. Okay. Then there's some things that we haven't talked about. Fatty acid biosynthesis. This requires acetylcoenzyme A. So later we're going to actually look at the other way around, breaking fatty acids down into acetylcoenzyme A. Question?
Is it still a catachloride?
Yes. Yeah, catachlorodic because we're going to pull out a citric acid cycle intermediate. acetylcoenzyme A is what it needs. Acetylcoenzyme A can't cross the membrane. That's not actually what gets depleted. What it does is it pulls citrate from the CAC, and this can cross the mitochondrial membrane, which is converted to acetylcoenzyme A in the cytosol. Okay, so if you have a lot of extra glucose around, you can upregulate synthesis of fat in order to store it. And that is done by pulling citrate out of the CAC. And then one more for our caloporodic. And that is amino acid biosynthesis. This depletes oxaloacetate and alpha-ketoglutarate. And these are easily converted to aspartic acid and glutamic acid. We are going to look at degradation of amino acids, and really the only difference between aspartic acid, glutamic acid, and oxaloacetate and ketoglutarate is one amino group, and that's it. And then you can also make other amino acids as well, but the one-step conversion is to these two. Okay, so those are all ways that we can pull, we deplete the citric acid cycle intermediate. But you've also got the anaplerotic pathways, and these replenish citric acid cycle intermediates. They increase the concentration. And we need this, okay? If we've got a lot of excess glucose, a lot of excess CAC intermediates, we can pull from it to synthesize things. But if you need to go the other way, if you need to upregulate the citric acid cycle, make it go faster, then you can do that by increasing the concentration of all the intermediates that are available. So you need those. And again, just a few examples. Your first step of gluconeogenesis again. Here's pyruvate to oxaloacetate. Okay. We can take advantage of the presence of that step in order to pull from the citric acid cycle, but we can also use it to put back to the citric acid cycle. Again, you have to use that malate aspartate shuttle to get it into the citric acid cycle, but oxaloacetate is intermediate. And then amino acid degradation. Again, we're going to talk about deaminations later on. And again, that's likely going to come in as fumarate, but there's a couple other places. So alpha-ketoglutarate, fumarate, but then you also get some weird things with leucines and isoleucines. All right, so that is the figure to know. So red is coming out and green is going in. So I'm depleting citrate for lipid synthesis. I am depleting, we didn't talk about this one, so acetylcoenzyme with the porphyrins, but that was on your question, I think, in the form but that's depleting, pulling away, so it's a cataplexy. If I want to, I can synthesize glucose. I can pull oxaloacetate via malate. Allergen is converted back into oxaloacetate. and I can pull amino acids from oxaloacetate, from alpha-ketoglutarate, and then here's the glutathione side, so leucine, combining some of the big hydrophobic branch things end up coming through succinyl chromosome A. Okay. We won't really talk about those pathways, we'll mention them, but we will look at the alpha-ketoglutarate later in the semester, and we will look at the fumarate later next semester. Okay. So those are your pathways. One more thing to note. Just notice that I haven't had two examples for that one. Fats do not directly replenish CAC intermediates, nor can they be used for gluconeogenesis. That's what I write. So even though we can pull citrate out to synthesize fats, we can't put it back. Fats get broken down to acetyl coenzyme A, and acetyl coenzyme A, although it can enter the CAC, it always consumes oxaloacetate to do it, so you never increase the number of CAC intermediates with fats. So you can store excess glucose as a fat, but you can't turn it back into glucose. You want to hear about the exam and the extra credit first, or you want to do your activity first?
Exam.
Yes.